You're very welcome back to the second episode of my new line of videos on Formula 1 parts. Now these series of videos are going to be concerning rare Formula 1 parts which wouldn't normally be seen, I guess, in the public domain or the general public and all that. In the first video I showed you the pneumatic valve spring and how that works and what it looked like and all that. So following on from that, as promised, in the second episode I'm going to do approximately a 45 minute video on the torsional damper, which was a key thing in the Formula 1 engines back, let's say, back to the DFV, the Cosworth engine, and many engines before that, aircraft engines and all that. And its job is, it's this here, its job is to smooth out torsional vibrations which exist in the crankshaft, mainly from the firing pulses. Now, in a perfect world, you would expect the crankshaft to turn around smoothly like that, but that's not the case. It actually turns in pulses to do with the firing order, you know. Once you get your explosion here, it gets a bang, you know, so that input force lasts a bit, then it relaxes, and then you get another one. So with the V10, which this damper is out of, I mean, you know, you've got 10 impulses into the crankshaft, so that's fairly noisy, you know. It results in the crankshaft winding up a small bit, unwinding and all that, and it's seen at the timing end where the gear drives go up to the head. So if that torque or turning vibration was allowed up to the camshafts and up through the gears and all that, it would break things. Now there's also torsional vibrations present in the camshafts too. Not so much as the crankshaft, but they are there. Now, there's obviously, which I'll go into in the middle of the video, there's ways around that as well to smooth out those. But it's mainly concerning the crankshaft. That's where most of the torsional vibration comes from. Now, this was an old jig that I used to display secondary vibrations in an engine. Now, they're slightly different vibrations in that they're a shake, for want of a better word, but it all results in varying impulses into the crankshaft. Now, I'm going to show you, I wasn't going to show you this jig, but for those of you that aren't mathematically minded, it might be something you've struggled with before. I mean, you know, we all know primary vibration, that's the general engine shake with the parts moving, but the secondary vibration is somewhat more interesting. And it concerns the crank and the slider mechanism, which has been around for ages, for hundreds and hundreds of years. But it's got a quirky, what would I guess, phenomenon, or not phenomenon, but a quirky feature that some of you mightn't be aware of. Now it's very easily explained in math. It's just basic triangles and all that. But for those of you that shy away from math and, you know, change channel when they see a whiteboard with loads of equations and all that, this is for you. You will understand secondary vibrations once I explain all this to you. So let's do that first, and then we'll dig into the damper. There's a very interesting part inside. It's like a Swiss watch. You'll love it. So stick with me on this, and you might be amazed. So I'll just run through it quickly. So this is a basic, let's pretend it's a Formula 1 engine cross section. There's your piston cross section. Apologies for the hands. I had a late one, just working on prototypes. So I said I'd give a video out once a week, so I'm going to try and stick to that. So there's your basic cross section, your piston, conrod, your crank, very basic. Now the only difference with this is there's a secondary rack here, as you can see, driving this pad here, and this rack is driven with a gear, a spur gear, on the underside of the crank. Now the important thing to know about all of this jig is, which I'll show you now, is the stroke of the piston is exactly equal to how much this moves in and out. Okay, that's all you need to know. So I'll show you when I turn it like this. If I just pull this here, you can see it moving. Okay, so the stroke is 69.08, which I'll explain to you why that is in a moment. So when that turns like that, you can see that also has moved to 69.08. All right, so that's very simple. I'll just bring it back to top dead center again. So the reason that's 69.08, it's no reason really. The spur gear that I had here, which drives all this, the pitch circle diameter of that spur gear was 44 millimeters. Now if you multiply that by 3.14, you get 138.16, which would be the circumference of that pitch circle diameter of the spur gear. Now if you divide that by 2, because we're only doing just 90 and 180, you get 69.08, okay, which is our stroke. And if you half that, you get 34.54, which is our throw. So that's all that math. Not important at all, but that's where the figures come from, if you're wondering. So just to run through why there's a weird phenomenon with the piston and slider mechanism, which causes the much hated secondary imbalance. A piston actually moves at a different rate. Even if this is turning at a constant rate, if the crank is turning at a constant rate, the piston, its acceleration is changing, its velocity isn't the same always. So I can demonstrate that now very easily. No math, no scary whiteboards, none of that, no equations. I'll just demonstrate it right in front of your eyes. So if I start to turn this here, now we'll just watch this for a moment, okay? You have this size here and this size here. You'll notice the first half to that line there is larger than the second half, okay? So let's turn that and see what happens. The piston is going down, all right? So we're at 90 degrees here on the crank, and you'll notice that the piston has traveled further than halfway, all right? So I'll explain why that is in a moment. So let's say we go to 180. Just keep going, which is there. So now it's at bottom dead center, and the lines match and all that. This gap is also closed now as well. It's traveled in 69.8. We'll get to that in a moment. So why is that? All right, so we'll bring it back to top dead center again. Why does it move? Even if it's connected to this, if this is turning at a constant rate, why does this move more for the first half than the second half? Well, you know what I mean, the first 90 and second 90. So let's bring it back to top dead center again and see why. So when we bring this down, this is moving out as well as over, okay? It's moving out this way, and it's also moving down to be in center with the crank center, all right, for the first 90, okay? So that's easy to explain and understand. It's moved down and it's also moved out, all right? Now, when I bring it the rest of the way, it's still moving down, but it's also moving in. Now, it is that in that's the important part. And why is that important? It's to do with the center of the conrod moving to the center line of the bore. Now, if I remove the conrod, you'll see it far clearer. If I just remove this for one moment and remove this, you can see the spur gear there. It's very simple. And I hook that on there again. And let's just bring it down to the center line of the crank. Okay? So if I move this out as it did to 90 degrees, right, I have to move it also down a small bit, like so, to keep it on center, which is where that journal is, the big end journal ends up when it's at 90 degrees after top dead center. So let's just do that again. I know I'll move it back, you'll see how much it goes. So let's just pretend it moves up 8 mil. So when that moves out, it moves the piston down. Let's just pretend it's 8 mil, okay? So that's fine on the top. So the second 90 degrees, yes, it is going down, but this is also returning to the center line position. So no matter what happens in terms of rotation, if this has to move back again, it will move the piston up 8 millimeters. So in this second 90 degrees to 180, the conrod big end is traveling in the way, so it's actually raising the piston up as it travels in. So that's why the first part of the piston's descent to 90 degrees, it travels more than the second part, because this is returning to the center line. Let's just go through that one more time, because it can catch some people out. So just pretend there's a slider here as well. So if I move this out along the slider, okay, it pulls the piston down 8 millimeters. All right. Now, irrelevant if the crankshaft is there or not, if I return it back then again along that straight line, it moves up 8 millimeters. And as I said, when it's going down here and around here, it is returning back again, so therefore pushing the piston up 8 millimeters. So how can we see all that, or how can we see what's happening in relation to, you know, the relationship of the travel of the big end and the relationship of the piston? Well, that's where this comes in, the rack. So if I return that there again, place this back in here again, which is pretty much top dead center there. That will go on there. Now, the one thing to be aware of, folks, there is play in all this mechanism. It's not machined at high tolerance. It's just machined very quickly for a prototype once upon a time, to describe to a few guys that couldn't wrap their head around the math. And it was just nice to see that they finally understood afterwards, you know. Now, it wasn't to do with an engine at all, but it was to do with a job we were working on, which involved crank sliders, and there was dampers on it, and they couldn't understand why the dampers were fine for one part of it and then they weren't fine for the rest of it. They just couldn't wrap their head around the math, because they just weren't maths guys. I'm not blaming anyone, you know. If you're not maths, you're not maths. But so now let's see what's happening. So if we move over here to this table, now I know you're looking at this table, you're going, geez, it's crazy, but it's not crazy at all. There's two very basic things in this table, and that's this dimension and this dimension. All right. So this dimension here is the stroke. All right. And we know that this moves in and out the same amount as the stroke. So that's that dimension there. So it's a square. Very simple. All right. Now, earlier on, I attached this stylus here to the piston, which I'll attach now again. And you'll see what happens. So this just screws on here. Now I should show you this actually. I had got a pin in there, a Sharpie. Now I just have a screw in it at the moment, because I don't want to draw on a second line, because it's a bit wibbly wobbly, the whole thing, because again, the tolerances aren't at all Formula 1, which is unusual for a change. So that screws on there onto the piston, like so. I'm going to put the tip of the stylus. If you pretend there's a pin in that again, the tip of that screw is right on the starting corner, right here. All right. So that's that. So we can tighten that up, hand tight. Fine. So now, what this stylus does is it moves both ways. Or sorry, it moves one way. This moves the second way. So as the piston is descending, the stylus would move from here to here, which is 69.08. We have it here, 69.08. Simple. It has to move from there to there. That's a given constant. All right. Again, when this moves in, the stylus has to move from here to here. Given constant. Has to do it. It's mechanically connected. So now, if the whole thing was linear, if the piston did move at the same rate as this was to move around here at the same rate, this line here would be a diagonal, but it's not. So we can very simply, they did this a lot with steam years ago, before they had electronics and all that. They had, I guess you'd call them analog plotters, where they plotted loads of different things. They were very cool machines, and which a lot of electronic machines were based on afterwards. Not the mechanics of it, just the principle of how they worked. But it's foolproof. Um, it can't fail, nothing like that, you know, and they work really well. They could work in all conditions. They were normally drums with a plotter pens, like an earthquake, you know, a drum when you'd see all the needles, and they were recording pressures and everything like that, and the drum would spin, and it would just record it, and you'd pull off your paper, and you could see it handed to the engineer, and they'd have all the different readings and all that. So this is kind of that way. It's very much analog. So just to say, we can now graph this here, what's going on. As you can see, it moves a lot in the first part and then not so much in the second part. So if we pull in that stylus and we pull the rack sideways, you can hopefully see it trace that curve. Okay, so you can see that curve tracing. Again, they're both constants, so it draws a nice little curve. All right, that's very simple, isn't it? So if we reverse it back again, which I shouldn't do, never turn an engine backwards, we can go back up to the top again. Just have a look at it one more time and do it once more so we can see that curve. Now I'm going to stop when I'm at 90 degrees here. All right, which is approximately there. So if we look in this axis, now this isn't drawn exactly square either. Everything is a bit out, but it's near enough to what I'm going to show you. So the travel here, this way, the screw is exactly halfway here and here. All right, and we're halfway to 180, which is 90 degrees. Okay. Here's a different story. We're halfway here, but we're more than halfway here. And as I said, that's because the conrod is not only going down, but it's also going away. So this has to come down the theoretical 8 mil we said. But on the second half of it, it slows down because it's again giving back that 8 millimeters as it comes back to straight on the bore center line, or I guess the y-axis, and returns again. Now if we stop it, if we go back again to 90 and stop it here, 90 degrees, halfway, and we bring a line out, we bring a line up to hit that curve and bring it out here, and we can see the differences, which is the same here, but now we have it on a graph. So I'll just pull that stylus off there again, actually take it off altogether, save a bit of confusion. So just to explain what's going on with this graph. So we've got a nice curve, and this is our halfway point on the crank, all right, 90 degrees. So you can see the piston starts, now this is, again, this is a constant. This is top dead center here, we're traveling this way in time to bottom dead center. And again, the piston is descending here to here. This is the first 90, more than the second, okay? So this is the acceleration graph and deceleration graph of the piston in relation to the crankshaft. Again, if it was linear, if they both moved at the same speed, which isn't physically possible, it'd be a straight line, but it's not. So as you can see, it starts off slowly, accelerating down, then it speeds up, speeds up, speeds up, speeds up. That's our halfway point on the crank. We're going farther than halfway down on the bore, and again, then it starts to slow down, decelerate to here. So that's why you get your secondary vibration, because the speed, like I'm using simple terms here, not to get into crazy inertia values and all that sort of thing, and angular velocities. So what's happening is there's a speed differential in the piston and the rate this is turning at. They're actually traveling at different speeds, both these masses. So they can never be truly balanced without balanced shafts. You can do it with balanced shafts, but they cost money and all that. But so that's just a basic rundown on the secondary vibrations or secondary imbalance. It's a very interesting thing. Hopefully that has described it a bit better than loads of maths and whiteboards and all that. Now you can actually see this here. You may have seen these in books when you're reading about, you know, secondary vibrations, first and secondary order vibrations. You'll see this here represented with maths. Now, obviously we've only went 180 and half a turn, but you might recognize it if it was brought up there. You'll see a load of those repeating, and then you'll see the first order vibration overlaid over it. So hopefully you now know where that came from. It's exactly it. It's just literally plotted, analog, there you go. No math or anything like that. Now obviously when you're designing an engine, you start with all this and you reverse it all back and you end up with the parts here. Now you might have a few constraints, let's say bore width or something like that, bore diameter, throw, but this is where you start with all the maths. But I just thought it'd be nice to see it explained maybe in a simpler way. If some of you guys tuners out there are reading books and you're going to yourself, what is this secondary vibration all about and why is it and all that, that's why it is. But now getting back to Formula 1. So with the crankshaft, as you can imagine, all these are inputting into the crankshaft at different times, obviously, with 10, you know, there's a lot. Now, the more cylinders you have, generally the smaller the cylinders are, so the less hammering the crank is getting, but they're still all there. And the other issue is, the farther away they are from the gear drive at the end, the more chance the crank has to wind up all along it. You know, like if the one here, the crank is very twisty here, as opposed to one here right beside the gear, which isn't as bad, it hasn't as far to travel. So you've got all that acting on the crank, and you get a whole lot of noise into the nose of the crank, and that noise has to be depleted with this guy, because if that makes its way up to the crankshaft or to the camshafts, it's going to do damage. You can snap camshafts, it's bad for valves, it's just not good. So what I'm going to do is stop the video for a moment. I'm going to get rid of this, if we're all happy, which we should be, hopefully. Hopefully that's made it really clear. If I had my way, I'd have one of these in every college in the world, just on the wall, that people could turn and see this, and it might give people a chance that thought they hadn't got a chance when it's represented visually. But enough of the talking about this. Let's pause the video and delve into this. It's magic. See you in a second. So here we are back again. Jig gone. Hopefully that's all in your head, and you might remember it a bit easier. So onto this guy. So that's the camshaft. I'll just leave that aside for a second, and that's the quill drive for the cam. So this was designed a long time ago. It's seen many iterations since, mainly by Cosworth, and obviously Honda. Everyone had their own, but this is the Cosworth item of the Cosworth TJ V10. It's the last of the greats, or one of the last of the greats. It also featured as well in the CA, the last V8, the Cosworth V8. They were pretty similar. Now obviously the innards would be different, because it has to operate at different frequencies and all that. Now I'm going to put up a picture now of the valve train and the gear train and all that on the front of the engine. So you should see that on your screen now, of the route of the power up to the top. So this sits somewhere in the middle. Now if I flip it over, it's gears and gears. So these are independent. This one is independent to this one. Now inside there's a flex system. So this can flex independent to this, and therefore dissipate the torsional vibrations, dissipate the energy as heat into the oil. Now this was, I picked this up, it was damaged. It was actually welded inside onto another quill for, I think, setting the timing on something like that. Just a mock-up for a timing jig on the engine. So ignore those beautiful weld spots inside. This sat on the front of the engine on a boss, on a shell, on a bearing shell, like a needle bearing, which I'll show you on the video now with just an image there. It was oiled. You can probably see the oil holes inside there. There's little oil holes there where oil was pumped into it to cool the insides. Now, looking at it, it's a very simple part. On the outside, there's nothing too fancy, but on the inside, it gets crazy. You can probably see the TJ numbers there on the edge of the teeth, along there somewhere. There's also various timing marks for the engineers to set up the timing of the engine. So this is together. I have all the screws removed. Now I may pause you at some point or stop it for a second to take apart the insides of it to show you it in depth. But this is together with a ring of countersunk Allens. They're M5s, which thread all the way through to here. So it's together pretty tight. So if I remove this cover, which is more than just a cover too. Now again, this is a extremely high precision bit of kit. So you can see the cover there and the innards, which we'll get in a moment. So this cover is also playing a part in the whole thing, which isn't apparent at the start. Now if you notice, if I just fit it on again, now it's not fully down its place there, but when it's in its place, there's a small gap between here and the face, which it mates against. And this is actually a spring, would you believe it? Which I'll explain now. So this can move independently to this outside gear. And that happens with all these torsion bars, which are here. So these little arms going out, they connect the inside gear to the outside gear. All right. So these arms also, because there's a bending moment in them here, these arms sit in little, let's call them aluminium bronze or silicon bronze cups, because there is a slight bending motion there, and the ends of the arms have to be able to flex slightly. They have to be able to steer in this outside gear. All right. Now, these torsion bars, these aren't actually the torsion parts, which I discovered later. Well, I just didn't discover it. I drew them. I measured them very accurately and drew them, and I brought them into CAD and did a simulation just to see where the torsion was happening. And it is happening on the bars themselves, which I'll show you in a moment. I'll pull out one, I'll show you. So these go down, they're like little L shapes. These go down and they're interference fit into the inside boss. You can see the squares there. That's how they locate. All right. So they're tapped in a neat fit, and they can hinge there. All right. So the twisting motion, the torsion, is actually present on the bar down along. It's not this arm that bends. So extremely accurate item, extremely high tolerance, and again tuned to get rid of whatever, you know, resonance or whatever frequency harmonics they want to get rid of at a particular point. Obviously they'd probably be fairly bad at idle, but a Formula 1 engine spends no time at idle, so they don't need to bother there, but it's normally up the range, at a particular range, where the most damaging frequencies occur. So this gets rid of them. Spectacular piece of engineering, designed originally by Keith Duckworth back in, I don't know what date, on the DFV. It was very similar to this. Obviously this has got a bit smaller, it's extremely small for what it is, but an amazing piece. But this, just to mention it, because there is movement between these two, that movement then in turn needs to be damped. So there's a phosphor bronze ring here, and that's the function of this spring washer. Let's call it a spring washer. And that goes down there like that against that and locates there, and it can, this is what's happening. If I exaggerate, this is what's happening as the engine is running all the time. This is getting rid of the frequencies, you know, and dissipating them as heat into these torsion bars. But this, if you want to damp it again, it keeps the whole thing from you know, buzzing, for want of a better word, uncontrollably. It'll be a bit like a damper on your car, you know. This damps the motion, the vibrating torsional motion. So that was very interesting. Not apparent at the start taking it apart, but apparent afterwards when you measure things, you know. But because there is motion between these two, there is a phosphor bronze wear ring between the two of them, you know, because there is motion there, and you can see the fretting on the outside where it sits against. You can see the fretting there, so it was needed. But as you can see, each of these oil holes, I don't know where the best place to see them. Hopefully you can see them at some angle. Somewhere there, very small holes. Each of those holes are opposite the torsion bars, so they pump coolant oil, or it's just engine oil, but cooling oil, should I say, just right at the torsion bars where they're the hottest, dissipating the energy. So that cools them, and then it finds its way out around all these and all that. There's an awful lot of force, rotation force will, that's spraying out the oil. So it finds its way out that way. Now, before I take this apart, I'll just give the camshaft dimension and the quill as well. Now this camshaft is from the V10. Now I've shortened this camshaft. Hopefully you can see the end there, the quill drive. This has been shortened. It would be, let's say, 6 inches longer or 5 inches longer. The gear drive locates in here. I'll just enter this in here now. Again, it's a precise fit. So that's the quill drive. So there would be another gear here on the end driving that quill. Now this quill is a torsion bar as well. Now there's loads of torsion bars throughout the whole engine, which I'll show you on the screen now, on the water pump drive and the oil pump drive. The shafts are wasted down and they're usually hollow. This shaft is hollow. So there's a certain amount of elasticity there as well in terms of torsion. Now, again, I mentioned that the camshaft has its own torsional vibration issues, but they're not as bad as the crankshaft. So this is fed into the cam here, which is a good idea, because the farther in you can feed the power, you know, the less elastic zones there are either side of it. Like if it was fed in the end, you'd have the entire cam would be elastic. But if you feed it in as far in as possible, you're shortening up the furthest elastic zone. So that's also a torsion bar as mentioned. You can see that the finish on it has been shot peened to compress the surface. It just makes it a bit tougher, resist cracking and all that. So that's another feature. It's the quill drive on the camshaft. Common enough in a lot of Formula 1 engines, you know, but something to note. So I think that's the camshaft fairly mentioned. Nothing like too exciting to look at, but very important at the same time, you know. Now some manufacturers, to get around the issue of camshafts winding up and all that, because they do wind up, they put a gear here as well on the end, which mated to the cam beside it. So it kept them in check from winding up. It kept them in time all along their length. That wasn't done on the Cosworth engine. They obviously got around it. Now, another thing to mention is as well, which is somewhat hard to believe, and it's the same on the crankshaft. Because the cam can wind up to a certain amount, the lobes are actually ground offset from the start point to the end point. They're ground at a twist, so that when the cam is loaded and unloaded, they actually end up in the right place. Now, obviously all of these things, you know, they restrict your accuracy of valve timing, because there's a certain amount of compliance in this. You know, let's say it doesn't move 5 degrees, but let's say it does, just to exaggerate it, let's say 1/2 difference. So if you have that possibility of variation in this torsional damper here, and you also have some in the cam which is under torsion or has torsional vibrations, and you also have some on the crank, there's a window of unknownness, you know, in terms of timing that you have to allow for, or the valves could kiss the pistons. So that's the one drawback of all this. Plus as well, you have your allowance of backlash in all the gears. Now, it wouldn't be so bad when the engine heats up, but cold, there'd be more, you know. But you can't be as tight with the timing, but you have to have all these items, you know. So it's a trade-off. But what I'm going to do now is I'm going to take this apart, pause this, take this apart, and just go through a quick rundown on all the parts. So I'll see you in a sec. So here we are back again. I got them all dot punched back. It's just basically a dot punch here and drive them back. So I can start to remove them now. They just lift up. I'll show you one in detail in a moment. Again, super high tolerance. These square holes here, this would all be CNC machined, as you can see with the tool marks, and the square holes then will be EDM'd out, which is electronic discharge machining, where it's like a piano wire is put through the hole, and there's a, I guess, a charge, for want of a better word, put through it like a welder, and it just spark erodes away all the material, so you get really accurate, you know, down to microns, less than that, you know. So super high accuracy, and you can do square corners and all that, or whatever your wire radius is, you know. So that's how the squares were cut out for those. So we'll keep taking them out. So again, the design, the machining of all these, astronomical at the time, you know. And here we are with it now. So that's them all out. Now you can see I can rotate them now because all the torsion bars are out. So you can see the movement, you know, independent to the other gear, the other side, which is machined integral to the inside boss. So now that's maximum movement. It wouldn't move that much, but you can see how much it does move, you know. So if I lift this up very carefully, I can place that there. We can have a look at this again. There's another ring here that it just won't come off. I'll just leave it there. It's just pressed on. It's just a wearing again for the truss face. It's quite tight, so I'll leave it there. But you can see the square holes that were EDM'd out, that they sit into. So yeah, beautiful part. Steel part, obviously. It'll be extremely high grade steel and ground and all that. But amazing part, you know. So that's that. That's the inside boss. These I have to be very careful with, because I don't want to end them up on the floor. So these are what the ends of the torsion bars locate into. They're quite small. Again, they're aluminium bronze or phosphor bronze. It's way higher material spec than that, but let's just call them that. So the ends of the little torsion bars will go in there. They sit in there like that, and they can move, you know. Again, as I said, I drew this part originally just to see, because it wasn't clear. It's clear now, obviously. If the torsion was occurring, if the arm was bending here, or if the torsion was occurring here in this section. And I knew straight away when I took them out, because of the high polish, that it was occurring here, you know, because the reason it'd be high polish so that it wouldn't fatigue, crack, or anything like that, or fracture. So you can see on the screen there now where the most stress is on them, and is where the oil holes are aimed at as well, which you may be able to see in there. It's just right at them to keep them cool. So that was that. As I said, you can see on the screen there the high stress area on the CAD, just on the simulation I did. So very interesting. Again, you can see the tolerance, you know. It's an extremely nice fit. So that's the torsional damper. Again, an amazing part inside. I don't think it has ever been seen before either, and cured the many issues that they had with various things breaking back through the years, you know, especially on the DFE. I know it caused awful trouble. I don't actually on the DFE it was designed in at all, and Keith came up with it probably one night in his sitting room when he went home. After he went home, he came up with the solution to isolate the torsional vibrations from the valve train. So again, hasn't changed that much. I don't want to put a picture of the original drive up. I have pictures of the original Keith Truckwood Design Quill Drive, but they're not owned by me, and I don't want to get into that. And I just want to keep it all here and keep it all local. So that's that part. I hope you enjoyed this episode. For the next one, episode 3 already, which is nice. I will probably do a video on the scavenge system on the Formula 1 engine. So that would cover, let's say, the sump area, the scavenge manifolds, and the scavenge pumps and all that, and show how that all works, with a few nice parts as well. So that's it, guys. Thanks for watching, and take care until next week. I shall see you again.